Welcome to the Cal Corporation's series of videos about software engineering. The topic of this video is Move Semantics. Before proceeding, make sure that you have already watched these other videos first. Some custom types are defined to own a large payload of data, which is computationally expensive to copy from object to object. Each object's payload was dynamically allocated, and the object was defined to have a data member pointing to its payload. This example client code is copy constructing a destination object from a source object. If your client code actually does need to do copy construction like this, then you have no choice but to accept the computational expense of it. The same is true if your client code actually does need to do assignment, which we will now more carefully call copy assignment. However, there are some situations where you don't need these full copy semantics. Instead, it would be enough to have move semantics. Instead of copying the payload from source to destination object, only the pointer is copied. This effectively moves the payload's ownership from source to destination object. The source object must be left in a valid state, though, which is accomplished by properly nulling it out. This function that used to be called a copy constructor is now called a move constructor. You can make the same kind of change to the copy assignment function, turning it into a move assignment function. Traditionally, a theoretical type was implemented in C++ via 5 functions: a constructor, a destructor, an equality operator, a copy constructor, and a copy assignment operator. If we think our client code might want move semantics, then a theoretical type is now implemented via 7 functions, the same original 5 plus a move constructor and a move assignment operator. Notice that a copy constructor and a move constructor can coexist in the same class definition. When it comes time for one of them to be used, the compiler chooses between them because of the usual mechanism of function overloading. C++ invented a brand new type for this, so that overloading can distinguish a desire for copying from a desire for moving. This new type is called a R-value reference. It is written using 2 ampersand symbols. If your custom type had a concatenation operation, then the result of that A plus B subexpression would exist as a compiler temporary object. In this example client code, that a plus b compiler temporary then gets assigned to the destination variable. Having a compiler temporary as an assignment's right-hand side is an ideal candidate for move semantics, because that compiler temporary will soon be thrown away anyways. Thus, for compiler temporaries like these, all modern compilers will give them a type that is an R-value reference. That will cause your class's function overloading to choose move semantics. Take a look at this example client code. This oSource variable is something that could be assigned to by writing it on the left-hand side of some assignment statement. Therefore, it is what we call an L value. For function overloading, it will match the traditional const reference, which we might now more carefully call a constant L value reference, not matching the R value reference type. As a result, copy construction gets performed. But what if the programmer knows that he will not need to use that oSource variable anymore? At least not in its current form where it's containing that data. So then the programmer doesn't need for data to be copied. He'd prefer the faster performance of simply moving the payload into the destination variable. To cause the move constructor to get called instead, the programmer is allowed to cast oSource into a R value reference type. So what happens if your client code passes an R value reference, but the CR type class was defined without move semantics? The answer is that your R value reference can automatically coerce back into a traditional L value reference type, and the copy constructor will get called, kind of as a fallback. Although we saw in our previous example that overloading preferred to match the R value reference type with its exact R value reference parameter type, if the class programmer had written both copy and move semantics. For the moment, think about things from the perspective of this client code's programmer, who might not even know how the class definition has been programmed. We know that if you merely pass oSource, then a time-consuming copying will always be done. But if you pass an R value reference, then either a copy or a move will be done, depending on whether that class programmer wrote a move constructor for us or not. So you, the client programmer, should think of this code as a request. I won't need oSource as it is anymore, so move if possible, but fall back on copying if that's all you can do. The responsibility of the class programmer is that in either case, the oSource variable must have been left in a valid state, so that either way, you, the client programmer, can still continue to use that oSource variable after this code has been done. However, because move semantics might have occurred, you, the client programmer, should assume that its payload might have been taken away from it, or maybe not. So you have to now treat oSource kind of like you would an uninitialized object once again. What about if the class programmer hadn't programmed neither copy nor move? In that case, the rule is that the compiler will automatically generate its own implementation of both a copy constructor and a move constructor. And then, since you're passing an R value reference, it will select the best match, which would be the compiler-generated move constructor. There is a new move function, whose implementation only does this typecasting into a R value reference for us. The convention is to use move instead of manually casting yourself, because its function name makes your intentions clear. However, be aware that this move function does not itself do any moving activity. All it does is a typecast, relying on overloading in your class's definition for any actual data movement to happen. We can generalize this idea of copying versus moving into the concept of accessing versus consuming. Here, we have two overloaded functions. Both are passed a reference to an object of our custom type. The first function only needs to access that object's data, but the second function might consume that data, taking its payload away from it. There's a quirkiness to watch out for when combining the concepts of R-value reference together with function parameters. Imagine that these two functions don't do their own work. Instead, we want them to each delegate to their own helper function. You might think that the delegation would be written this way, but this is wrong. When we call the consuming version of do function, we're passing something that is a R-value reference type. That's what allows overloading to select the correct do function implementation. The ARRO object formal parameter receives what we pass, but beware that the ARRO object variable is itself a L value. It is a variable name. It is something that could be potentially assigned to on the left-hand side of an assignment statement. So during the process of invocation of this do function, we've had something automatically convert from a R-value reference matched with a R-value reference parameter type, but then automatically converted by the compiler into an L-value type. Consequently, this code, as currently written, will call the wrong helper function because it's currently passing an L value to the helper function. There is a simple solution to this issue. Even though the process of parameter passing converted ARRO object so it's not a R value reference anymore, we can simply cast it back again when we need to. Traditional C++ categorized its expressions as being either an L value or an R value, depending on whether or not that expression could be assigned to. Modern C++ splits that concept of an R value expression into X R values, which are expressions that manually became R values, such as our manual typecast into R value reference examples, or pure R values, which are all remaining R value expressions, such as the expression 1 plus 2. STL has implemented move semantics for its collections. If you might want to use your custom type as an STL item type stored within some STL collection, then your type's move constructor and move assignment should be marked as no except.